Yo, yo, what's up, what's up, what's up? Welcome back. Today we're working on my x86 operating system. So we have this like little dummy OS. It boots in QEMU. It does like some memory allocation. It does some logging to like the serial console as well as to like a virtual monitor. It has unit testing. It has the ability to read and write the RTC clock. It has the ability to work with PCI and has like Rust's async await support in there, so we can write like async functions. And what we're working on today is trying to finish up our Ethernet driver. So we're writing a driver for, hold on, let me find the right window. This one probably. We're writing a driver for the RTL 8139. Which is this like old ass PCI card that is apparently like baby's intro to Ethernet device programming. So that's where we're starting right now. We've kind of like figured out over the last few streams how to like read and write to it. We have a driver that has these like write and read APIs on them. The read function says like I'm gonna wait for some data, and on read I'll call this callback with like with a slice that will be deallocated when I'm done. And the write function says like here's a packet, and I'm gonna write this and wait when I'm done. Then you can drop me, right? And this is great. These are working. If I run my little demo, here I like read the MAC address from the network card, and I send a packet here. We find it. We write out a long test string that is over 64 bytes long, else it will crash because Ethernet frames are typically 64 bytes long. And then we read that back, and we actually do that in parallel, where since these are like using async, like we can have this guy waiting on a read, and this guy will sleep and then write it a second later, and that's all working. But the problem is, in order to accomplish that, we have to break some of Rust's mutability guarantees. So Rust has these rules that say, like, we can only ever have one mutable reference to someone. And this write function requires a mutable reference to self because he has this, like, internal counter that says, like, how many things have I allocated? And in reality, maybe we should also have a mutable reference on read, just because like these things are like interacting with device state, and if multiple people were trying to like change device registers at the same time, that would be like a problem, right? And so like really this should be mutable as well. And so then the question becomes like, how do we interact with this thing? Right? Because if we can only have one mutable reference, and we're gonna want to be able to send packets and receive packets independently, how do we do that? And so that's what I want to like work on today. I suspect that the answer is going to be some form of like interior mutability and like mutexes that can be unlocked, but like async mutexes, because these aren't actually running in parallel threads. They have to be pulled to see if they're available and woken up by the executor, etc., etc. So what we have right now is we have this like read function, and the first thing we have to do is find like some safe way to block on a packet without locking up all our data. And maybe we should have some sort of like condition variable as well that like will signal to this guy when he's ready to be written. I'm not sure. We'll think about that. So really the only thing here is this get packet call just pulls these in order to like start waiting. He just pulls these two registers, and he sees if they're close to each other. So really what we could do is, in our spitballing here, we could move this like waiting out here. Right, we could do this. Or we could move this here. Then we could like have lock our mutex in order to do this part. Then lock it again to do this part. Maybe, right? That's kind of what I'm thinking right now. And then we can, if we had that mutex, we could like mark this guy as immutable, and have interior mutability through the mutex, right? And that would be pretty cool. Probably we can also have separate mutexes for reading and writing. I would assume that the registers that we're looking at for reading are different than the registers we're looking at for writing. But probably we'll actually want to like keep track of which mutexes or which registers we're using for what and lock them independently. All of that's kind of up in the air. That's just kind of what I'm thinking right now. But all of that has to come through the implementation of like an async mutex, which we don't have right now. So I haven't really thought about this too much, but I suspect that an async mutex is actually going to be quite easy to implement. I think all it is a number. We can have like, let's open a new file here. Source util async mutex. I think we could probably just in here, we'll have like a mutex that's wraps some type t. And probably, hold on, let me just fix this error message. We'll just pub mod async mutex like this. We'll have like the inner value, which is a t. Unsafe cell t probably, but we'll get there later. And I think that all we have to do is we can say count. And this count is how many people currently have him locked, right? And then what will happen is when we poll our future, so how these like Rust futures work are we have this like struct, and basically we just call this method on him and we say like, are you ready? So we'd have like impl core future for mutex t, where this is implemented for all t's. And he's going to ask me to implement this poll function. And basically all I do here is I say like, when I am ready, I will return my locked thing. And when I'm not, I'm not. And I think all I really have to do here is I say like, if my count is 0, then like I'm ready. Otherwise, poll me later, right? I actually think that's it, surprisingly. And I think here my output would be like mutex mutex guard t with a lifetime of a, probably. I think this is how they implement it. So like what happens is this guy, you can't access the guy inside without locking him. But when you are ready, you get like a reference to the thing inside. So I'm just thinking out loud here. I think also probably this is a long-lived thing that is not a future, and probably this guy will actually have an async function on him called lock. So we'll have like a implementation for this mutex t for all t's, and we'll have this function lock, and he takes himself by immutable reference because we have like many guys looking this, and he returns a mutex guard t, probably, and our mutex guard is going to contain a reference to inner and a reference to cell count, I think. Presumably. Let's think about this. So what happens is we call lock. This is an async function, lock. We do this check where if count is 0, then we're ready. Otherwise, we create the mutex guard and increment the count. So we say this is actually no longer for the mutex. This is for like a mutex locker. And he probably doesn't actually need the type in here. He probably only needs this like count variable because this is the only thing that determines if we're locked or not. So this guy just returns nothing. And let's think about this. Sorry. brain is not working all the way. Yeah, so he takes in, he's going to return nothing. And he's going to have a reference account, right, like this. Which is a usize, which means that he needs to have a lifetime attached to him because he doesn't know how long it's going to live. And we need to specify any lifetime here. We don't really care what it is. Okay. So now we say if self.count is 0, then we're ready. Else, we are pending. So we need to import the Rust core future poll. No, core task poll, maybe. Yeah, nice. And these guys need to be poll ready and poll pending. Okay, so this is like my first attempt at this. Now we would like instantiate this mutex locker. So we'd say mutex locker self count await, right? And if we increment the count, right? And if we implement the count, then we're ready to return the thing. So we return our mutex guard. Inner is self inner, count is self count. Now, there's some obvious problems with this. One is that these guys are immutable, and we need these to be mutable somehow. So the primitive here is Rust has this like unsafe cell type that says, I know the rules here. I will not break the rules. I promise you that you will only ever get one mutable reference to something, and I'm going to enforce that myself. So I think I can just say import cell unsafe cell, right? And here I can like put these guys behind unsafe cells, and this will tell the compiler that it is okay for these might be modified between reads, and you should be aware of that, and you should not do optimizations that will conflict with that, right? Now all of a sudden, I can hand out these mutable references to the things inside, and I think that nothing will go wrong. Now let me think about this a little bit. So the assumption here is that this like async lock is actually not going to be sendable, but it will, or syncable, right? This is not something that is used to synchronize between threads. It's just a way for us to provide interior mutability by waiting for somebody else to be complete. So that means that we need to make sure that we have not send on mutex or mutex guard. So mutex t, and negative bounds are not fully implemented. Use marker types for now. So I guess I need to make sure that these are not sendable, and I'm not actually sure if they are. So let's see if unsafe cell is sendable. Or let's actually just look up send. I want to make sure that there's no way to transfer this between threads. So these are, in fact, everything inside is sendable, because this is like a T, assuming T implements send, this will implement send, and that's a problem because we don't want it to, because this count is a usize. So is there like a marker trait for not send? Is there like some sort of like phantom? So send is implemented for phantom pinned. Can I implement not send? Rust force not send. How to implement not send or not sync for a type? Phantom unsync, phantom send. Okay, so they're saying that the guard is not sendable, and it's okay. So I guess maybe unsafe cell already is not sendable. Let's check that. Impulse send for unsafe cell if the inside is sendable. Yeah, so we need to like manually make it unsendable, but it looks like they've already made it non-sync for us, which is good. I guess we could argue that send is okay, just that sync is not. So we're probably chilling. We are probably chilling. So let's... It's interesting. How come they can do this? Implement not sync for unsafe self T. Why can't I do that? Right? That's what I want to do. I want to say impl not send for mutex T. Or for mutex guard T. I guess for both. Negative trait bounds are not yet fully implemented. Negative trait bounds are not yet fully implemented. So what do they say? Phantom data const, sure. Okay. That's fine. We'll just do that for now. So we'll say phantom, or we'll call this not send, is phantom data. Oops, crashed my language server, so we'll just restart real quick. I think it's like phantom data. Where was this? Phantom data. Core marker. So we have a marker, phantom data. Oh, this actually did manage to get imported. I just didn't see this. And we will just say that this is not sendable by marking it with phantom data const this, because that's not send or sync. And we'll do the same thing for the guard. And because the reason for that is these guys are going to be like, I'm worried about the mutex being sent but the guard not or something, and like these two guys ending up on different threads. Not that we have threads at all. I'm just trying to, like, in the future I'm going to get lost by this, so I'm just trying to make sure this is ironed out now. And this way we can make sure that the guard and the mutex are always on the same thread because they can't move between threads. Easy peasy. Okay. I guess maybe you can't move something while you have a reference to it, actually. I actually don't know how that works. Anyway, so let's just do this for now. And now we can assume that here we are the only person writing because we're in a single thread. We don't have to worry about synchronization. We can just increment the count. So we say self.count.get plus equals 1. Actually, this is a problem, right? Because you could have two people waiting on this at the same time, but they will never both unlock at the same time because there's only one thread. These are not sync. Perfect. And so now all I have to do is set this as phantom data. And this guy is get. We have to call get like this. Dude, I've been doing a little Haskell this week, and now I see mutable async state, and that gives me shivers. Yeah, I apologize. I get the feeling, man. I'm shivering too. So it looks like this all works out now. And I think that this is all I need to implement like a way for me to get interior mutability on my type. So let's just go back and go to main. And maybe what we can do is we can try to like hold a mutex. We can maybe try to test this by holding a mutex for a little bit and seeing if that fixes it or changes anything. No, I'm just gonna run it. Do I want? No, I will. Okay, fine, we'll do it. So we'll say we'll make two features, right? We'll make this like locked is an async block, and he's going to create a mutex. So actually, he's going to use a mutex. So we're going to have a mutex shared between these two async blocks. We'll say let x equals mutex, which needs to come from my crate. So we'll import it. So we'll say use crate util async mutex, and we'll make this mutex new 5, right? We'll let him be an integer. Probably this is going to get mad now because this mutex is a private struct. It also has no new function. There's a lot missing here. So this guy needs to be public. This guy needs to be public. This guy needs to be public. And we need a pub function new, which will take in a t and return a mutex guard, or a mutex, sorry, of type t, which is just mutex inner count is initialized to 0, and not send is phantom data. I think for a little bit of extra safety here, we can say self.assert or assert eq self.count.get is going to be 1 after this. We need to make sure that we're not double incrementing somehow, which I think will be hard, wouldn't work, but just double checking. And here we call into to turn these into unsafe cells. Like this. Okay, so now we're going to call this, we're going to lock x, and we'll say locking x, like this. We'll lock it. And then we will sleep for 5 seconds, which is just take this sleep block and run it for 5 seconds. And now we're going to we're going to make a try lock, which he sleeps for 1 second, and he says trying to lock x, right? And we'll print after that he's done. Print acquired. Now, if we run these two futures, lock and try lock, what we should see is we should see one guy start waiting. He should lock and then say sleep for 5 seconds. And then we should see after 1 second trying to lock and acquired. So let's just take a little attempt here. So we'll run the executable, cargo run. And he says locking, sleep for 5 seconds, trying to lock X. And nothing's happening. Obviously. Because I never free the lock. I'm an idiot. Okay, so not here. This isn't the driver I'm looking at. Here, I need to say that when I drop this guard, I decrement the count. And I also need to be able to like interact with the number in it. So first, let's say impl dref for a mutex guard. At, where this takes in an A and a... Maybe I only need to do T here, and I can say... I wonder if I can just say this. Just implement this for everything. Fuck you, I don't care. Let's see if he lets that happen. So, he actually does need... maybe this needs to be a lifetime. Cannot find trait dref. Okay, so ops dref is where I get this from. And I do need the type parameter T here. It's not letting me use an anonymous type. Okay, and now I can implement the target. So this is T. Dref gives me a reference to T. And this is just self.inner, easy, as an ampersand. Oh, actually just self.inner because it's already a reference. Okay, now we need to do the same thing, but for dref mute, which I think is dref mute like this, no target, and dref mute like this. And I think this is probably like this. Probably. Let's see. It's gonna yell at me. The compiler's gonna get mad. So dref mute actually needs to be of type mute self. makes sense. And now it's complaining that the type count is never read. And this is the part that we have to fix, is we have to make sure that when we drop this type, our guard, which now needs my like t here, because it's nipple for all types. This is a drop function that takes in ourself by mutable reference. And I think it's just a self.count minus equals 1. And here we should assert that the count is 0 after this. Otherwise, we don't understand something correctly. This needs to be dereferenced. And this also needs to be dereferenced. Okay, so now let's try that test again. And what we hope to see is that after like 4 more seconds here, it should acquire the lock, which it does. So that's pretty cool. We just kind of like bullshit our way through a mutex implementation, and it actually looks like it's working. I wasn't expecting that to go that well, which is pretty cool. So maybe what we should do is we should write some tests here. This is actually something that's really, really easy to write a try-lock function for, which makes unit testing also really easy here. Assuming that my test infrastructure allows async, which it does. Very cool. So let's actually bang that out quick. So we'll make an function try lock, which is the same thing, except it returns an option, mutex guard, with a lifetime and type t. And this actually does the same thing. So maybe we'll make a function, instead of this await, we'll just run the check. So this actually is not an async function. This is just an immediate thing that happens. And we'll just make a function in here, unsafe function acquire. And this is like the part of this that is going to be the same between the two parts. So the two different versions, I mean. So this is this. And that means that we have to increment the count and return the guard, right? That's that. And so now from this lock version, we call self.acquire. And here we'll also call self.acquire. But instead of this, we're going to call essentially this, which means that we need to split out this logic into a function, which is going to say what's it going to be? It's going to be function is lock ready. Rust traits are kind of sick. Yeah, they're pretty sick. I like them more than like in C++. You have these like general inheritance, and you also have like compile time like templates and stuff. And the way Rust does it with these like traits where they're both compile time and runtime, and you don't get these like inheritance trees. You only get like, I implement this trait. I think it's like very nice. It's kind of like the best of all worlds is how I feel about it. But yeah, they're pretty sick. Pretty sick. Okay, so here I'm going to say is lock ready, and we're going to take in the count as a u size. And if the count is equal to 0, we return true. Or is lock free, we'll call it. Else, return false. Easy, right? And so now we say if is lock free self.count. And now we do the same thing. If is lock free self.count, I'll just return count equals 0. Yeah, sure. You're right. It would get mad at me if I, yeah. Good point, good point, good point. Otherwise, we return none here. Okay. Arguments of this function aren't right. Why is he bitching? Self.count is an unsafe cell, right? So I have to say, get like this. Raw pointer is unsafe. Okay, I get it. Okay. So now that I have like a try lock function, I should be able to get away with writing a unit test to deal with this. Oh, this also needs an unsafe block up here. And so now I can just say config, what is it? Config test, I think. Mod test. And I use everything in the parent module, and I also use everything in my testing module. And we just pull out a sample from somewhere else where I wrote some unit tests. Probably in here. Create test. Where have I written some tests? Here we go. We'll just pull an example out. And we're going to make a test called test async lock, right? We don't have to get crazy here. And inside, we'll just do something very similar to the test that we were doing before, where we acquire lock. Different lines. Let guard 1 is we lock, right? First, we need to make a locked thing. Let guard 2 equals x.try lock. And we should test that guard 2 is none, right? Because we expect that this lock will fail because this is not available. Then we'll drop guard 1, and we'll try this again, and we'll say this should now be sum 5. Sum 5 is wrong. We need to dereference this. We'll do this. Well, we'll see. When I run cargo test, it'll tell me what I need to fix. So here he doesn't like that guard 2 cannot be formatted using debug. So let's just fix that here. We'll just say derive debug. I don't really care if the details are leaked. We also need to derive EQ, partial, EQ, etc. And now he's saying that I compared with sum 5, but it's actually a mutex guard. So we'll say if guard we'll say if guard 2 is none. No, that's not what we'll do. So we'll say let val equals match guard 2. And if it's sum v, we'll return v. If it's none, we'll now return an error saying unexpected or guard 2 should be available. And this must be a string. Okay, so now we have the guard for real. And then we can say that we test that guard 2 is 5. Oops, that's the wrong thing I just typed. So let's kill this and cargo test. We're getting close. We missed a semicolon here. And 114, he doesn't like this because he can't tell which type none is. That's so stupid. I don't understand why this keeps happening, but if I just do like A equals B on a option type, it can't tell what the type is. So we'll just say test true, guard 2 is none, and that will do essentially the same thing for me. Okay, so we have a sign that this is working, and now let's delete, disable this drop, and we should see it fail, just for confirmation that it's not good. And it says, yep, guard should be available, so we're failing correctly. So I think we're chilling here. That's like a really basic quick test to make sure that this async lock is at least like blocking me out when what it should be. It would be nice to test the waiting logic, which I actually think is doable. So we'll say this is test async. We'll test try async lock here, and we'll test async lock down here, and we won't use the tries at all. And what's interesting here is we can actually make two futures that run in parallel since our tests are running in the context of an async executor. I think what we can do is we can say we've acquired the lock, and we can wait for 5 seconds with one future and bail out if that's happened. So we can use, I think it's future select, is going to wait for one of two differently typed futures to complete. The function will return a new future which awaits for either one of both futures to complete. The return future will finish with both the value resolved and the future representing the completion of the other work, right? So I can say guard 1, and we can put one async block in here that just tries to lock it again, right? And we could put another one in here that sleeps. However, I'm remembering now that the sleep implementation requires a bunch of state that we don't actually have here. So I'm going to just leave this for now and assume that the try lock test is like sufficient for what I care about for now. Obviously, it's not perfect, but it's something. So let's kind of assume that this async mutex is complete for now. We're just having about 35.5. And now let's try figuring out how to like make this RTL driver actually use that mutex to support reading and writing in parallel. So probably the write call is going to want to lock everything. The read call is going to want to lock everything other than get packet. Or sorry, other than this receive waiter. So it's going to wait once it's ready, then lock. Let me think about that. No. We could just try lock, and if the lock fails, then say that we're not ready. That's even easier. I like that. That makes it very, very, very straightforward. So here we'll make a inner struct for our driver, right? And what I like to do when I do this is take the implementation of everything here and move it into the inner version. And then we can use like these like mutable, immutable things on here to kind of flag what we want. And we can like avoid like keeping the locking logic in here and stuff, which makes things nice. So write needs to be mutable, and really let's just make everything, like we'll make read mutable. It doesn't matter because we can't access the inner thing without locking, so really all of these can be mutable and it doesn't matter. But we can do that for sanity. So we're close here. This guy returns an inner. None of these guys are yelling at me. And now all of these guys just forwards. So the we'll say that inner is inner new PCI interrupt handlers with loopback like this. And we return now an OK RTL 8139 inner. Easy peasy. Now we delete all this code. Boom. Done, done, done. And we just need to delete the semicolon. And we do the same thing here. This guy is a now immutable thing. This guy is an immutable thing. And the write function, sorry, 1 second. This needs to be inner, like this. The write function will do the same thing, where we call a self.inner write packet. Except now we actually have to start worrying about the mutex locking. So I actually completely forgot even to put this in a mutex. So this should be mutex like this. And we use our crate from util. We take in async mutex. Right? And now we say mutex new, inner new here. And here we just say lock. Easy. Right? And here we do the same thing. Self.inner.lock.read on read. And even here we do the same. The MAC address could probably have been done without this, but I'm okay with just locking inside. So this is async as well. Like this. Cargo check. I'm sure that there will be compile errors now because in main we deleted some code that wasn't being used now. So we have send and receive now. Okay? And now all we have to do is move the waiting code outside. So here, we can unlock as we do not lock this until we know the buffer is ready to be read. And we have this like receiver waiter thing already. So all we have to do is pull this out of here. Right, like this. And maybe even we should really have a way to like do an action while we wait. Like unlock the mutex for this action, but I'm not going to worry about that right now. I know it's like kind of like a shitty API, but we can always come back to it later when we inevitably introduce races with it. But also it's harder to introduce races with this type of mutex because it's there isn't actually other code running at the same time, right? Because it's a single-threaded mutex for async code. So I think it's actually okay to do this. So we'll say that the base, we'll just pull this out temporarily, even though this is kind of like subverting the mutex. I'm kind of like admitting to myself that I know how to, this is like, I'm being careful here. So we'll lock the mutex just to get the base value of it. Right now, we can initialize this thing. And we should be able to trust now that here we'll be able to lock the mutex. Maybe not, because there could be multiple people running at the same time. So we'll actually probably want to do a loop here. So we'll say match the try lock here. And if we get something, so we get some value, we can do v read. And if we get none, we do nothing. We continue. So this has to be done in a loop, right? Because if we fail to get the lock here, it means that somebody else beat us. And now we just have to break the loop here. Like this. So we're getting close. This needs to be a wait. And here we can replace it with a if sum mute v equals this. Let. Sorry, I forgot the let there. Okay. So I think now if we go back to main, we should be able to remove these unsafe cell hacks that we were using before. So we can get rid of this. All of this goes away. Now we get rid of these like hacky gets and stuff. Like this. Like this. There we go. And there was one on the logging of the MAC address as well. And it looks like it compiles. And it looks like it ran okay. That's very cool. So we now have like simultaneous reads and writes. Very cool. Very, very, very cool. I'm pretty happy with that. So that actually was a lot easier than I thought it would be. Yeah, that's waiting for a second before writing and then printing it. Very nice, very nice. So let's make a checkpoint there. And we'll say async mutex in RTL 8139 driver. Cool. Cool. So now that we've kind of handled that, we have some like driver cleanup to do. So the first problem is on write. Where do I find this? On write, we're supposed to cycle through these like 4 transmission buffers, right? And if we don't, if we loop through all 4 and the other one's not done yet, we'll actually just overwrite ourselves. Now, let me think about if this is actually a problem. Since write is mutable, we can only have 1 packet writing at a time, which arguably is a bad API, right? Really, we should be able to have 4 writing at a time. But since we only have 1 writing at a time, that means that this, to transmit data and wait, will prevent anybody else. It'll prevent us from clobbering ourselves because we won't finish this write until we have finished sending it. So I'm actually okay with that. So this actually doesn't need to be done, which I'm surprised by. I kind of thought that it would, but I've kind of talked myself out of it just reading through it here. Another problem is that when we instantiate this device, the first thing we do is we like look up a device ID. And if we like find a device that has like, let's see if we can find the implementation of this. We get a device that has like a specific PCI bus address. So like a bus and slot, it's like we're kind of saying we are in control of this PCI card. But then like somebody else could come and they could do the same thing, and they would find this. They would like get the same device, and we'd be like fighting with each other over the same device. Now, what I don't know what to do though is, once we get the device, we actually don't need to interact with the card through it for a while, because we call this like find mmap range function on it. And what happens is we have CPU, and he talks to details. We're skipping details here. He talks to PCI, who talks to the card, net, who talks directly back to the CPU. And so what we do is we ask the PCI bus for the address of this network card in our memory, and then just interact with this like directly. And so the question is, how can we enforce that we keep only one person owns that memory? Which is hard, right? Because we're just doing like raw pointer access. But it would be nice to have some sort of like registration mechanism just to avoid accidentally double dipping on device drivers. And so probably what we would have to do is we would have to make memory accesses go through the PCI device that we hand out, right? So like we're going to get like a PCI device handle, and we're going to we'll get like a PCI device handle, and if we accessed all memory through it, then we could say that like you don't ever get to see the memory directly. You just get to write into offsets into that memory, and I'll keep track of it. And that way I know that nobody else is writing to me, because they could have some sort of like registration system to handle that. So let's take a look and see if that's like feasible. So on my PCI device, instead of having this like find mmap range, maybe we we can still say find mmap range, but this mmap range won't make its internal details public anymore. it will just have a function that is write, and hold on, let's think. We'll have an mmap range, or mmap range might not be the right name for this anymore. And we can have a function on him to like write and read memory from it. So we can just say like function read u8 from offset. Maybe we just want read 8. Read u8, sure. Where the offset comes in as a usize. Right? And he returns... What does he return? A u8. So we could like make read and write functions, and this guy would be doing like a self.start add offset read volatile. Right? And let's see. Does that make sense? So here, that does just give us what we want here. I'm okay with that. So now what we can say is if all of our memory accesses go through these like functions of the guy, then we can't just hold onto the pointer and we have to hold this guy. And this guy will know how to unregister himself from like the allocated devices list when he's dropped. I think that works for me. So let's just start by moving all of these functions into here. And instead of working with the base directly, we'll work with these instead, which is going to be a little bit of a slow, painful refactor, I think. So we'll call this mmap mapped memory or something. And he is a mmap range. And that mmap range comes from PCI, so we'll pass this in like this. And now we just have a fuck ton of details to deal with. So function length, he returns a usize, which is just his length. Right, no need to get crazy here. So now we say this guy can just call this function. He can say if my length is not equal to 256, then we have a problem. This is to be a public interface. And this also has to be a function call. Now we start saying that our reset device, now instead of taking in the base, he takes in the mapped memory, which is an mmap range. And instead of saying base.add register offset to get the register offset, he will just, well, I was going to say that we're going to use the offset directly in here. Does that make sense? I think it does. So we can say, here, we'll say mapped mem read u8, and this is from command register offset, and this is the same as what we had before. This should be mapped mem, not mapped mem. Okay. We're getting close. So we go PCI, and this now needs to be a public function. So pub unsafe, I think, or unsafe pub. That seems good. And now we'll add a write u8. So this takes in a offset and a val. And we just say write volatile here instead. Mapped mem write u8 at command register offset val. Right? And then we do the same thing here. Mapped mem read u8 at command register offset. Now, where this is getting kind of nasty is we have to like pass in this command register offset over and over and over again. You could maybe like abstract this in some way where you get a reader for a specific register by like requesting that from the range somehow. Like you could have like a I don't really want to deal with that though. I was gonna say you could like have some functions like get subs get reg who returns a like with a size parameter that returns a like mapper of with size, and then that has like a get and a set that takes in the size thing. But I think all of that starts to add more complexity than is worth. I think I'm okay with just spamming these like register offset constants everywhere. Will live. Okay, so now reset device has to take in the mmap range as a reference. And let's just keep going. So mapped mem is a reference to mmap range. Here we need to do the same thing, so we pass in mapped mem instead of the base pointer everywhere. And here we need to use the mapped mem, which is a mmap range. Okay. Mapped mem, and this now needs to be written and read as a U32. So we need to add these same functions, but for U32. So we can replace U8 with U32 here. And these starts now have to be as we need to add in these as star mute U32 like this. Right? Right, volatile. Now what we're seeing here is that we could probably get through this with some macros. Right, we could say like macro rules impl type, impl mmap type or something, right? And what he has is he basically has these two functions, but he implements them based off of the type. So we have type, I think it's like type is like how we flag to the macro system what this is. And oh, ty, not typ. And now we just start throwing in the type in here. So we say here t goes here, t goes here, and t goes here and here. Now it gets a little tricky because we need to like concat the type name with the rest of the macro, or with the function name, but there's this like paste macro that lets me do that I am importing. So I think that the syntax is we take in like this, and we can just say t like this. I think. We'll find out. Okay, so now we say impl mmap type, and we'll just put in a U8 here, and a U32. Okay. So that we make like short bursts of progress, I'm going to leave these types as public, and that will let us slowly work through these one by one without losing the ability to compile. So let's leave a cargo check here and see what ends up happening. So lots of problems here. Self.base unknown field. So let's, in my RTL 8139 driver, instead of only preserving the mmap range, we'll also, let's take the base. Cargo check. We're a lot closer there. We have these guys. He expects a mmap range, not the base pointer. And here we have mmap mapped mem is mmap range, and base is mmap range start. Okay, so I think, do we compile now? Almost. We have these functions up here that have not fully been finished, so this guy is where we were before, so he's going to write to mapped mem write u32 rb start offset. He's going to write to the rb start. He's going to write the adder as a u32. So that's what we had here, but we're just doing it the new way now. And the new val is the same thing, where we say mapped mem read u32 from the rb start register, and we insert the same. Okay. So what doesn't he like here? Arguments this function are incorrect. It's because this is taking in by value instead of by reference. Cargo check. And we need a like clone Aroni around here somewhere. So that's in 345. Cargo check. Okay. And if I run this, everything's still working, so we haven't broken anything yet. And as I work through this, I'm starting to think that this is extremely boring. So what I'm going to do is I'm going to keep going through this process off stream, go through the same thing. But for maybe I'll finish this part later. So we'll get comment-m starting to use mmap range instead of base pointer. And the idea now is let's get into actually how we would handle device registration or like memory map range registration. So I think that's the interesting part of this. So we have this type, right? And now that we will in the future force ourselves to do all reads and writes through that, which means that we'll have a handle to all reads in the device. And that means that when we drop the handle to the device, once we drop all handles to the device, we can consider that free for use again. So what we could do now is we can have in our PCI subsystem, we can have a like allocated devs, which is just going to be a hash set of PCI addresses, probably. Right? And what happens is if we find that device in that set, we'll just reject it. And when we drop everything, when we drop all of the pieces, we'll remove it from the set. Now, that means that this needs to be shared between all of the types that are kicking around, and probably statically shared with like some reference count. Otherwise, how will we remove ourselves? And it needs some sort of synchronization primitive. So let's just for now do rc ref cell. Which says like we don't actually need to synchronize. We'll just be very confident that when we drop these things, we're dropping them from the scope where there will only ever be one mutable reference to this. So we'll use core core. What is it called? Alloc maybe? Alloc rc, and we need to use core cell ref cell. I believe are the two. Right? And then for the hash set, we need to use hash brown hash set. Okay, so what happens here? First, we make the allocated devices. So is rc new. It's a new rc reference counted pointer, which has something with interior mutability, which is a hash set like this. And then we can provide this to the constructor, and we're chilling here. So now, when we try to find the device, before we do this, we insert him into the allocated device list. Now, we can't actually insert Sorry, let me think about this. Thinking. Yeah, okay, so that's fine. So here, here we've just used the address, but we haven't actually done like an upgrade on it, and that's where we're gonna have to actually insert. Well, like here we have an address, but we're not using it. After we turn this into an actual PCI device, then we are. So here, before we return, we'll just say let ret is this, and we'll turn ret. But before we do, we need to add the address to the set. So we'll say let allocated PCI allocated devs insert. I guess first we have to check if it's in there. So we'll say if it contains or borrow has contains. Why is contains on there? Well, we'll find out. If it contains myself, we panic for now. Not device already in use. And actually, now that I'm getting here, I'm kind of realizing that the logic of like unregistering a device is something that we don't need, right? We're never dropping devices right now. We're only instantiating them, and we just want to make sure that we're not instantiating the same one twice. So I think it's actually fine to just do this. No shared state. And just if somebody tries to allocate the same device twice, we tell them to like screw off. And in the future, if we actually want to handle like dropping device drivers and that type of thing, then we'll deal with that at that point. But there's no reason to do this now. And really, you could argue that this is like a programmer error for now. In the future, we may not, but for now we do. And so we're kind of actually fine, right? This is actually all we need to do. Hold on, I need to add some derivations to this guy so that he can be used as a element in a hash set. And there, I think we're actually done. Let's just do a cargo run. Yep, and now what we should do is if we, in main, we try to allocate a second driver, we should panic on the second one, saying that handlers should only be registered. Oh, it's actually having other problems here. But hold on. Here, I would think that the device upgrade here would fail the second time. So let's... Oh, no, because we don't actually insert it. So now we just say POCI allocated devs insert self clone. We need to be able to clone ourselves, so we'll add a clone here. And now if I do this twice, the second one should crash. Device already in use. Perfect. And I'm okay with that for now. This is obviously problematic in that in the future, we're not going to be able to, like, what if you have two devices with the same vendor ID? What if you allocate the driver, drop it, and then allocate a separate driver with the same piece, right? Like, there's all sorts of reasons that doesn't work. But what's important is that it's good enough for now. And with that in mind, I was also worried about, like, when I shut down the driver, the card will still be writing to invalid memory. But again, we can just ignore that for now. And I'm happy to do that. So I actually think we're in a good spot. And I'm going to handle like the rest of the kind of like boring cleanup of the driver off stream. And call it for today with a short one there. Appreciate anybody's tuning in. Next up is probably going to be Ethernet frames handling and like maybe trying to build up UDP and TCP. Yeah, so catch me live on Twitch at like 2 Pacific time-ish, and if you miss me on Twitch, you can catch me on YouTube. YouTube is linked in the Twitch description. Twitch is linked in the YouTube description. Thanks for watching. Catch you on the next one. Bye!